Okay, thank you. Good morning, good afternoon, good evening, according to your specific time. I feel privileged and honored to present this research work in this International Water Conference organized by University of Oklahoma. My name is Yemane Gebraselassie. Currently, I'm working at Adama Science and Technology University in Ethiopia. This research work was part of my PhD study, which was conducted under supervision of Dr. Fallaka Zauga, the General Director of Africa Center of Excellence for Water Management, Professor Takattale Johannes, as well as Dr. Shimalis Kabada. Our research area was on textile wastewater treatment using hybrid solar-powered electrocoagulation and electrooxidation system. Here are the presentation outlines. So as an introduction, as we know, one of the major challenges facing mankind today is to provide clean water to a vast majority of the population around the world. And this need for clean water is particularly very critical in third world countries. This is because rivers, canals, and other water bodies are being constantly polluted due to indiscriminate discharge of industrial wastes through point and non-point sources. Among these polluting industry, textile industry is one, which is the large consumer of dyestuff, chemical, and water. Because of this, the textile industry is considered, because of this, it generates large volume of wastewater. If we see, for example, the application of dyestuff at the dye processing unit, out of the total applied dye, 30% of it will be remained unbounded to the cotton cellulose fibers, which means this textile industry is a significant environmental concern. Also, the textile wastewater is characterized by high value of pollution signs like COD, strong color, heavy metal. It has also low biodegradability and has high toxicity. So to remove those pollutants generated from textile industry wastewater, different technologies has been implemented or tested so far. Among these, physical-chemical treatment, advanced oxidation process, adsorption or nanofiltration, and biological system are among the few technologies. For example, if we see for the physical-chemical treatment system have a good removal efficiency. However, it has limited use due to its high amount of chemical required during the process and due to its large sludge production. And also, if we see the biological process system are considered not suitable for textile industrial wastewater treatment. This is because since textile industry uses chemicals, so those chemicals are toxic to the microorganism and high resistant for biodegradation. Sorry. However, recently considerable attention is given to those electrochemical wastewater treatment technologies. Their attractiveness is due to their less chemical requirement, less space requirement, as well as easy in operation. In addition to this, due to restricting environmental regulation and laws, the technology like this electrochemical technology are considered as a clean technology. Out of those electrochemical technology, electrocoagulation and electrooxidation system are considered as an efficient technology to treat textile wastewater for textile wastewater. Even though the two electrochemical technology are effective in treating textile industry influence, however, this cannot be achieved with a single method and reasonable cost. So recently, with different naming like hybrid, combined, integrated, dual stage process of electrocoagulation and electrooxidation have been attracted by many researchers to treat wastewater influence from textile industry. And what are really the literature gaps that we have identified during this research study? As we know, electrocoagulation is very effective only in removing colloidal and suspended particles, but less effective in removing stable persistent organic compounds. But for electrooxidation alone as a separate technology is very effective in removing all pollutants, including those stable persistent organic compounds, but it requires long operational time, which is less applicable, practically less applicable. So even though different research works have been reported on the combined process of electrocoagulation and electrooxidation process, however, this research vary regarding to the working condition and also the dye types they used, and also the concentration of the dye. The other research gap is the experimental research approach, which is one factor at a time. So most researchers, they are using this one factor at a time approach, and this experimental approach may result in the inaccuracy of optimal operating condition because of ignoring or disregarding the interaction effect between the input parameter and the responses. However, in this study, in our study, we have incorporated the interaction effect between the input parameters. In addition to this, even though there are studies that have been carried out on treatment of textile wastewater using hybrid electrocoagulation and electrooxidation process, but the dye concentration which are considered in those studies is, most of those studies, is less than 100 milligram per liter, which is below the actual dye concentration discharged from the textile industry. However, in our research, we have considered equivalent dye concentration to the dye concentration discharged from textile industry. Furthermore, the current big concern on energy crisis and climate change encourage researchers to use renewable energy. In addition to this, the evaluation of optimal operating condition for real wastewater and treatment cost analysis using detailed mechanistic study and using advanced instrumental techniques like IR spectrum and NMR spectrum are among the good strengths of this research work. So to answer the research gaps that we have identified, we have prepared some research questions. One is, what are the optimal working conditions for each treatment technology? How effective are the optimal operating conditions to remove pollutants from real textile wastewater? How well is the treatment technology performing in terms of mineralization and dye degradation extent? Is the solar energy an effective energy source? Can it be used also as an alternative source power to conventional electricity? And also, is the cost of operating the technology feasible compared to the other treatment technologies? So again, to answer these research questions, we have set some objectives. So the main objective of this study was to investigate the removal of pollutants from textile industry wastewater by hybrid solar-powered electrocoagulation and electrooxidation system, so as to overcome some of the fundamental limitations associated with former studies and also with the existing commercially available technologies. Here are some of the specific objectives, and I will discuss each and every one in the result discussion. When I come to the experimental setup and procedures, we have set two different experimental setup. One is for the electrocoagulation process, and the second is for the electrooxidation process. From this, you can see some of the experimental setups for electrocoagulation process. So for the electrocoagulation process, we have used rectangular shape aluminum electrodes with an effective area of 65 centimeters squared. The treatment system was conducted in a batch system, and the volume of the reactor for this treatment system was 600 ml. And we have evaluated the performance of the treatment system by applying current between 1 up to 3 ampere. Similarly, for the electrooxidation process, we have used rectangular shape of electrode, but here it was perforated or mesh iridium oxide coated on titanium and aluminum electrodes with an effective area of 48 centimeters squared, and effective volume of the reactor was 400 ml. For the photovoltaic experimental, we have installed the solar panel at Addis Ababa University, Department of Chemistry, with 20-degree inclination and north orientation. Again, we have adopted this formula to calculate the total operating cost of the treatment system. When I come to the result and discussion, the first objective was about investigating and optimizing the optimal operating condition for electrocoagulation process for the first treatment. And among those methods, especially for the optimization process, ANOVA and RSM were considered to examine the interaction effect between the input factor and the responses. And we have established the best operating condition of the treatment system. And finally, we have achieved only 89% of color removal and 76% of COD removal using this electrocoagulation process at these optimal operating parameters. And also, we have studied the kinetic study of the electrocoagulation process to see the absorption mechanism and involved reaction pathways. And under the optimal operating condition, what we did was first we have calculated or determined the amount of coagulant generated from each anode electrodes at different electrolyte time, and we use this coagulant generated as an absorbent, so as we can use it to calculate the total absorption capacity of the treatment system. Then the reaction-based pseudo first and pseudo second order kinetic model was adopted to determine the removal mechanism and rate of removal. And the best fitted model was selected according to the R square near to unity and less variation between the absorption capacity of the experimental and the calculated value. So as you can see from this table, the pseudo second order kinetic model was in line with the experimental results, which means the chemical solution mechanism controlled the removal of the dye from the wastewater. This result means that the exchange of electrons among the metal ion and the dye molecule are the cause of the electrochemical coagulation process. Second objective was to investigate and optimize the operating condition for hybrid electrocoagulation and electrooxidation process, and we have found 97% of both color and COD removal at these optimal values. For the mineralization study, we have used TOC reduction to evaluate the mineralization study of each treatment system, and we have compared the performance or the effectiveness of electrocoagulation and hybrid electrocoagulation and electrooxidation process in terms of mineralizing the dye through the TOC analysis. So as a result, using the electrocoagulation process, only 47% of TOC reduction was observed. However, 97% of TOC reduction was achieved using the hybrid electrocoagulation and electrooxidation system. For the dye degradation extent, we have used a combined instrumental analysis using FTIR and NMR instruments. Why we use these two instrumental combination? Because, for example, under a complex textile influent condition, we may see multiple IR spectra can be overlapped, making it difficult to describe the spectrum. Similarly, with this complex mix of compounds in the wastewater, we may also see relatively low resolution resonance in the NMR spectra. So to overcome these two problems, so combining the two spectroscopy instrumental analysis is very important, very important. So from this graph, as you can see, the graph A is the IR spectra for raw wastewater, and B is for the IR spectra of the treated wastewater. And from the treated wastewater, we have seen or observed the absence of peaks at 1,600 and 1,635 wave number, which shows that there is a breakdown of amine function and aromatic rings. This result also confirmed by the output of the NMR spectra. As you can see from this graph, we haven't seen any chemical shifts from the NMR graph. That means that all the aromatic and the amine groups are completely mineralized. So from this, we can conclude that through the TOC reduction, IR and NMR analysis confirm that all pollutants from the textile wastewater are entirely degraded into carbon dioxide and water. The first objective was about evaluating the optimal operating condition using real wastewater from textile industry. Why we evaluate the optimal operating condition using real wastewater? Because compared to the synthetic wastewater, the real textile industry wastewater are more complex in composition and contains different inorganic and organic compounds. Therefore, it is important to perform the technology and check the optimal operating condition using a real wastewater. So as you can see from this table, the removal efficiency using these two different sources of wastewater shows that a significant difference on the efficiency or on the performance of the treatment system. So from this, we can conclude that the technology shows a promising result and will work and can work for textile wastewater treatment. The fifth objective was about the operating cost using conventional electricity. So for this purpose, we have considered the cost of consumable chemicals, electrode cost, energy consumption, as well as the cost of sludge disposal, so as to determine the total operating cost. So the total operating cost of the hybrid electrocoagulation and electrooxidation system was estimated with at $1.4 per meter cube, which is still lower than the combined electrocoagulation and ozone treatment system and electrocoagulation and Fenton process as well. When we see the removal efficiency of those optimal operating conditions directly powered by solar energy, what we did was first we have calculated the total energy required by the treatment system and the total energy generated from the solar panel. And we have determined the energy used by the treatment system relative to the energy produced from the or harvested from the solar panel, and we have found that only 30% of the total 30% out of the total energy produced from the solar panel was used by the treatment system, which shows that the solar energy can run the treatment system. Again, if you see and compare the removal efficiency of the treatment system using different sources of power, like the conventional power source as well as solar power source, so you can see that the removal efficiency of each technology shows insignificant difference in performance using these two different sources of power. Also, the total operating cost of the hybrid electrocoagulation and electrooxidation system was $4.21, which is higher than the conventional source of energy, but still it is less than the coupled electrocoagulation and ozone method, as well as the hybrid electrocoagulation and Fenton process. However, we need to be in mind that this is the initial investment cost. So unlike the conventional electricity power, the advantage of using solar power is that there is less operational cost, less maintenance cost, and also it has less or no energy bills coming every month. So if we use this renewable energy. As a conclusion, we have only achieved 89% of the removal and 76% of COD removal using electrocoagulation process, and also we have achieved only 47% of TOC reduction using the electrocoagulation process. However, a complete mineralization was obtained by the hybrid system. In addition to this, the difference in removal efficiency using conventional electricity and solar power was insignificant. Therefore, this technology can also be used for treating wastewater using solar energy. As a recommendation, since this treatment system or this experiment was conducted using a batch system, so to integrate the result of this study into industrial application, it is recommended to further investigate the performance of the treatment technology in a continuous system. So I will finalize my presentation by depicting some of the future outlooks, even though some of them are already started. So according to the results, this technology is a promising technology which can be completely mineralize the wastewater from textile industry. Therefore, it is important again to test at a pilot scale or with large volume of reactors, so as different stakeholders or sectors can use this treatment system for their influent treatment. And also, we want to expand this research for further pollutant removal, like geogenic pollutants, for example, fluoride, arsenic, and others. And most of the influent treatment in my country, Ethiopia, are biological. Therefore, we want to introduce this electrochemical technology in Ethiopia. So finally, I want to acknowledge Africa Center of Excellence for Water Management for financing this project, and also I want to acknowledge the organizing committee of this conference for giving me this chance. Thank you very much. This is all my presentation. If you have questions and comments, please, you are very welcome.